The metal was not on fire. There was no flame, no arc, no visible heat source anywhere in the room. The steel inside the coil simply began to glow from the inside out, heated by a field of energy the men working around it could not see, could not feel, and could not measure with any instrument they owned. But the first time the lining cracked and the liquid metal hit the copper coil, the steam pressure had nowhere to go except outward. If you're new to steel and sweat, this channel covers the machines and the men of American industrial history, the things that built the country and what those things cost. Subscribe and leave a comment below with the next story you want us to dig into. This is the story of the electric induction furnace, the machine that melted specialty steel with no flame and no arc and no warning, and the refractory lining that stood between liquid metal at 2,800 degrees and the water-cooled copper coil wrapped around it, separating a functional furnace from a steam explosion inside an enclosed shell. But here's what the Bureau of Labor Statistics Foundry Injury Surveys from the 1920s and the National Founders Association safety reports from 1918 to 1928 document together that neither states outright. The induction furnace arrived in American foundries with an invisible failure mode that produced no visible warning before the event, no rising flame, no audible change in the machine's operation. The furnace that had been running correctly, producing a clean pool of tool steel or spring steel or high alloy composition in total silence, could cross from normal operation to steam explosion in the interval between one heat check and the next, because the lining between the metal and the coil had eroded below the thickness required to contain the charge, and nobody in the building had a way to see it. To understand why American foundries adopted this machine anyway, and adopted it rapidly, you have to understand what it solved. In the first 2 decades of the 20th century, American specialty steel production faced a quality problem that conventional furnaces could not reliably address. Tool steel, the steel used to make cutting tools, drill bits, and dies that had to hold their hardness under repeated mechanical stress, required precise alloy chemistry and precise temperature control during melting. Spring steel, armor plate, and high-speed cutting alloys were the compositions that the expanding machine tool industry and the emerging automotive industry required in volume. All of them needed a melting process that could hold a narrow temperature range, avoid atmospheric contamination, and produce a consistent charge every time. The open-air crucible furnace, which heated from outside through fire or resistance elements, introduced inconsistency through atmospheric oxidation and temperature gradients across the charge. The cupola furnace, which circulated heated air through coke combustion, introduced carbon and sulfur contamination that degraded the alloy compositions the market required. What is the practical difference between a foundry that can produce consistent tool steel and one that cannot? It is the furnace. What the specialty steel customer needed was a furnace that heated the metal from inside the charge itself, uniformly, without combustion, without atmospheric exposure, and with a temperature range that the operator could control with precision. In 1916, a Princeton University physicist named Edwin Fitch Northrup built the machine that could do that. Northrup had spent the previous decade as a professor of physics at Princeton after co-founding the Leeds and Northrop Company with Morris Leeds in 1903. In 1916, he was introduced to Dr. Gilliam Clamer, who ran Ajax Metal Company in Trenton, New Jersey. Ajax had been founded in 1880 by a scrap copper dealer and had grown into a serious industrial materials producer. Clamer wanted a better furnace for melting specialty alloys. Northrop had been studying the conversion of electrical energy into heat through electromagnetic induction. The result of their collaboration was patent number 1,189,725, filed with the United States Patent Office and issued July 4, 1916. The patent examiner in Washington initially rejected the application as inoperable. The claims Northrop made, that alternating current passing through a coil could generate heat inside a metal charge placed inside that coil without any direct contact between the coil and the metal, struck the examiner as physically implausible. Ajax's patent attorney arranged a demonstration at Princeton's Palmer Physical Laboratory. Northrop took an earthenware pot, wound it with several turns of ordinary lamp cord, inserted a piece of metal, and energized the circuit. The metal became red, then white, then formed a molten pool. The examiner allowed the patent with broad claims. What he had watched was the foundational demonstration of a technology that would be installed in hundreds of American foundries within 20 years. The physics of the machine is the physics of the transformer, applied in a configuration the transformer's inventors had not intended. In a standard transformer, alternating current in the primary coil creates a changing magnetic field that induces current in the secondary coil. In the induction furnace, the secondary coil is replaced by the metal charge itself. The copper coil surrounding the crucible is the primary. The metal charge inside the crucible is the secondary. Alternating current through the coil creates a rapidly reversing magnetic field that penetrates the refractory lining and couples with the conductive metal inside. The magnetic field induces eddy currents, circular electrical currents, flowing through the charge. The metal's own electrical resistance converts those currents to heat. Joule heating occurs inside the metal itself, distributed through the charge, with no contact between heat source and material. Time magazine, in a 1942 article on induction heating, described it plainly. Stick your hand into a large electric induction coil and nothing happens. Then stick a steel rod into it and the metal becomes red hot almost at once. This is the fact that the men working around the first industrial induction furnaces had to internalize without any prior experience to draw on. The heat was inside the metal. Nothing outside the metal was hot. The coil wrapped around the crucible was cooled by circulating water. The refractory lining between the coil and the charge was a ceramic insulator. The room temperature around the machine was normal foundry temperature, which was warm but not dangerous. What was happening inside the crucible, where the eddy currents were converting electromagnetic field energy into heat at a rate sufficient to bring 500 pounds of steel to 2,800 degrees, was invisible to every sense a worker possessed. How do you develop a safety instinct for a hazard you cannot see, cannot feel, cannot smell, and cannot hear? How do you maintain vigilance around a machine whose failure mode produces no visible precursor? Leave a comment below. The answer that experienced induction furnace operators developed over years of working the machine was simple. You watched the lining. But in the 1920s, watching the lining meant visual inspection between heats. Visual inspection of a refractory crucible between heats could not reveal the erosion that had occurred in the lower section of the lining during the previous melt cycle, because that lower section sat below the molten metal surface and was inaccessible during operation. But the early adoption period, 1916 to the mid-1920s, introduced a second problem that the lining visibility issue compounded. Northrop's original patent operated at frequencies between 20,000 and 80,000 cycles per second, generated by spark gap oscillators. At those frequencies, the skin effect, the tendency of high-frequency alternating current to concentrate near the surface of a conductor, limited effective heating to thin charges. The spark gap furnaces of the earliest commercial period were useful for laboratory work and small-scale specialty heats, but 20 pounds of metal was the practical ceiling. For industrial foundry use, the technology needed power sources capable of generating strong currents at lower frequencies, 1,000 to 12,000 cycles per second, where the electromagnetic field penetrated deeper into larger charges. Those generators were not available until the early 1920s, developed in part through Northrop's collaboration with Charles Steinmetz and the General Electric engineering staff. When generator technology caught up with the furnace design in the early 1920s, the industrial version of the induction furnace became viable for charges of 500 pounds and more. Ajax Electrothermic Corporation, formerly established in Trenton with Northrop as its head after he left Princeton in 1920, moved to install machines at foundries across the northeastern United States. The applications were precisely the specialty steel categories that conventional furnaces could not serve reliably: tool steel, spring steel, Alnico magnet alloys, high-speed cutting steel, and the high-purity alloys required for the vacuum tube manufacturing that Westinghouse was scaling at its Pittsburgh facilities. Every one of those applications required the clean, precisely controlled melt that induction heating provided. And every one of those installations introduced the lining failure problem into a foundry that had no experience managing it. Here is what the refractory lining was asked to do. It had to be thin enough that the electromagnetic field could penetrate it without significant attenuation and couple effectively with the metal charge on the other side. The physics of induction heating required the lining to be as thin as practical, but it also had to be thick enough to contain liquid steel at 2,800 degrees against the combined attack of thermal cycling, chemical erosion from slag and impurities in the melt, and the mechanical stress of the charged material shifting and settling during successive heats. The lining was doing both jobs simultaneously, and they worked against each other. The thinner the lining, the better the induction efficiency. The thicker the lining, the longer before it eroded through to the coil. Thermal erosion was the primary mechanism. Silica refractory, the material used in early induction furnaces for ferrous heats, begins to soften above 2,700 degrees. At the temperatures required for tool steel and high alloy production, the inner face of the lining was working at or above its thermal limit with every heat. Chemical erosion accelerated that process. Slag, the layer of impurities and oxides that floated on the surface of the melt, attacked the refractory chemically, dissolving the silica matrix at the lining's upper boundary. Mechanical abrasion from the charge material being loaded and shifted added to both processes. The lining that passed visual inspection after one heat might be at the edge of containment failure by the third heat of a shift, with no external indication of how thin the remaining section had become. But the bridging hazard introduced a second path to the same failure. When solid charged material, scrap steel or alloyed stock loaded into the furnace, failed to fully melt into the pool below, and instead formed a bridge across the upper section of the crucible, a gap opened between the bridge and the molten metal beneath it. The lower bath, still under full electromagnetic power, continued absorbing energy with no cold charge above it to moderate the temperature. It superheated. At temperatures well above the designed operating range, the lower lining eroded at a rate that could breach containment in a single heat cycle. When the bridge finally collapsed, the solid charge fell into a bath operating hundreds of degrees above normal pour temperature. The collapse could fracture a lining already thin to the edge of failure and drive liquid metal into a crack that the preceding heats had opened. If you're finding this history as important as anything we've covered on this channel, go ahead and hit subscribe now and leave a comment below with the next story you want to see. When liquid metal reached the copper coil, the sequence that followed was governed entirely by physics, and it ran faster than any human response could match. The induction coil was hollow copper tubing, water-cooled at a continuous flow rate to protect it from the heat generated in the coil itself during operation. When liquid steel at 2,800 degrees contacted the copper's thermal conductivity transferred that temperature to the water inside the tubing in a fraction of a second. Water boils at 212 degrees Fahrenheit, and liquid steel runs at approximately 2,800 degrees. The temperature differential was roughly 2,600 degrees. The water did not gradually heat and boil. It converted to steam instantaneously, undergoing a phase change from liquid to gas that expanded its volume by a factor of 1,600. A machinist who witnessed a coil breach at his foundry in the 20th century described the result as spewing molten steel into the air like a Hawaiian volcano erupts lava. The expanding steam carried liquid metal with it. Everything in the ejection zone received it. What induction furnaces in the 1920s did not have was a ground leak detection system. Modern induction furnaces incorporate a probe in the bottom of the furnace lining connected to the electrical ground that detects when metal has penetrated the refractory to within a measurable distance of the coil and shuts off power before the breach is complete. The system works by monitoring the electrical continuity between the molten bath and the probe. When the metal touches the probe, the circuit closes, the detector registers the contact, and the power supply cuts off. Without a functioning ground leak detector, a furnace with metal at the coil is a furnace running at full power on a breach that has already occurred and that the operator cannot see. The first indication is the explosion. The foundries installing Ajax Northrop furnaces in the 1920s did not have the system. The ground leak probe was a later development, introduced as the industry accumulated field experience with coil failures and began engineering a response to what that experience had documented. In the decade of adoption, the safety case for the induction furnace rested almost entirely on the operator's ability to read the lining condition from visual inspection between heats, to manage heat cycles to prevent superheating, and to recognize bridging before it progressed to containment failure. What does it mean to rely on accumulated operator experience as the primary safety system for a failure mode that produces no warning? All three required experience with the specific machine, at the specific foundry, and with the specific charge materials. The experienced operator of a furnace that had been in service for 1 year was substantially safer than the newly assigned operator of the same furnace in its first month of production. The difference in outcome between those two operators was entirely what they had learned to look for. Some learned from events recorded in National Founders Association safety reports and from foundry injury studies by the Bureau of Labor Statistics that aggregated those events into frequency rates. The Bureau of Labor Statistics began its first annual survey of injury frequency and severity for manufacturing industries in 1926. The 1942 Bureau of Labor Statistics study of foundry accidents, Bulletin 805, surveyed 2,188 establishments, and it documented the injury frequency rate for steel foundries at a level that placed them above most other manufacturing categories. The foundry industry as a whole had accident frequency rates exceeded only by logging and sawmill operations among manufacturing industries during the 1942 survey period. The induction furnace was not the only hazard in a steel foundry. It was one of several, but it was the one with a failure mode that produced no warning and that the workforce had no sensory way to detect, making the danger invisible. What the induction furnace produced, beyond its failure mode, was the specialty steel on which American industry depended for the categories where quality could not be compromised. Tool steel from induction furnaces held its hardness through thousands of machining cycles where lower grade material would have failed. High-speed steel cutting tools made from induction melted alloys ran at speeds that drove American machining productivity above what European competitors could match. Alnico magnets, developed in the early 1930s using Ajax Northrop furnaces for their precise alloying, became the foundation of American electrical instrument production. When Westinghouse needed the high purity metal required for vacuum tube elements, the induction furnace was the only melting process that could provide it. By the time the Second World War began scaling American armaments production beyond anything the economy had previously attempted, the induction furnace was in service at foundries, arsenals, and naval facilities across the country. The centrifugal casting of gun barrels, the heat treatment of shell noses for armor-piercing penetration, the surface hardening of tank track components and aircraft-bearing races all required the speed, precision, and metallurgical cleanliness that induction heating provided. The 1942 Time article documented that more induction equipment had been installed in the United States in the previous year than in any prior 3-year period. The machine that had been a laboratory curiosity in 1916 was moving the metals that moved the war. But the men who operated the furnaces at maximum output on wartime production schedules were running machines at the upper edge of their design envelope, on charge materials and alloy compositions that pushed lining performance to its limits, in facilities where the experienced operators had in many cases been transferred to military service and replaced with workers who were new to the specific machine and to the specific failure mode they needed to watch for. The ground leak detection systems that would eventually make the coil breach detectable before it became an explosion were still years from standard adoption. The BLS was running its wartime injury data series and finding frequency rates that the foundry industry would spend the following decades working to reduce. The Ajax Electrothermic Corporation continued operating in Trenton, New Jersey until Dr. Klamer sold the company in 1959 to Magni Thermic Corporation. By then, the industrial induction furnace had been in continuous development for 40 years, and the ground leak probe, the closed-loop cooling systems, the automated lining inspection protocols, and the operator training programs that accumulated field experience into documented procedures had changed the machine's safety profile substantially. The physics had not changed. Water at the coil still became steam at 1,600 times the volume in a fraction of a second. The lining still eroded from the inside during every heat. The refractory still had to be thin enough to let the field through and thick enough to keep the metal in. That fundamental tension is in the machine's design. Edwin Fitch, Northrop, died in 1940. He'd spent 20 years as the technical head of Ajax, building the high-frequency induction furnace from the laboratory demonstration that convinced a skeptical patent examiner into the industrial equipment that was melting American specialty steel at scale. His name is on the patent. His physics is in the machine. The men who worked the furnaces he designed are in the BLS Foundry injury records and in the National Founders Association safety reports, documented by injury type, shift classification, and whether the event was a lining runout, a bridging collapse, or a coil breach. The machine had no flame, it had no arc, it made no sound that indicated what was happening inside the crucible. The heat was in the metal, and the men who worked around it learned to read the machine's state through instruments and through the accumulated knowledge of what the lining looked like when it was at the edge. Some of them learned that from experience. Some of them provided the data point that taught someone else. The machine that produced the invisible heat is still in service in foundries today. The men who ran the early furnaces are in the BLS records. If this kind of history matters to you, subscribe to Steel and Sweat and leave a comment below. Thank you for watching.